All right, what is a compression ratio? How does it affect performance? And how do you figure it out? Okay, so compression ratio is the volume of how big the cylinder is when the piston's all the way at the bottom versus the volume when the piston moves back to the top. And you've got all that air squished up in here, up against the head, and all the space that it has is this space in here. So you put volume 1, which is the volume when the cylinder is all the way at the bottom, and you figure the volume by just measuring the depth of this versus its radius, and then of course you do pi r squared and so forth and so on. And then this, you do the same thing. You just measure length times width times height and figure that out. And then you put the volume 1, which is the piston at the bottom, over volume 2, which is when the piston's at the top and it's all squished. And after you do that, you divide the number on the bottom into the number on the top, and it will give you your compression ratio. So for example, in this engine, this is the math. We get 103 325 millimeters over 18,000 and change. So this would be the volume of the big cylinder when the piston is all the way at the bottom versus the volume of this when it's just squished up against the head. And so this divided into this, we get 1 on the bottom, of course, and then we get a decimal on the top. We get approximately 5.6. So the compression ratio of this engine is 5.6 to 1. And a lot of times you'll see compression ratios listed as a single number. Like if you Google something, they'll just have a compression ratio of 10. What that really means is it's 10 to 1. They're just not listing the 1 because the second number is always a 1. But in order to have a ratio, you got to have two numbers. So I like to list it as something to 1 just because it's the mathematical accurist in me. But anyway, this is what a compression ratio is. You figure it out by taking volume 1 over volume 2. And then you simply divide volume 2 into volume 1 to get rid of this big gnarly number right here, and you get something smaller like this. Now what does this have to do with my performance? Well, the higher this number on top, the more burn you're gonna get, the better the air-fuel mix is gonna burn. Because like I was saying earlier, the more pressure something is under, the more it wants to explode. So the more you can squish that air-fuel mix, the better the burn you're gonna get when it actually does explode. So in high-performance cars, you'll see compression ratios of like 11.5, 12.5, 13, and that's all. And those are high performance engines where you're getting really good gas mileage and really good horsepower out of your engines. Now this engine, as you can see, has a compression ratio of 5.6 to 1. So this is not a high performance engine. Even the lowest compression ratio in a car these days is about 10 to 1, unless you're talking about something rarefied like a turbocharged application or something like that. But so this comes nowhere near the efficiency of a modern car engine. However, for its purposes, it's perfectly fine. You don't want it to be super high compression because it doesn't have a gearing system, and by keeping it lower compression, it's not as hard on the engine when you're dealing with something like a lawnmower engine that's going to take a lot of abuse. It's not a high performance application. It's air cooled, so you keep that compression ratio lower, and that way it gives your engine a little bit of a break. Because again, the more pressure you put this under, the better your burn, but also the more heat you're generating, because the more energy is being emitted by the actual explosion when it happens. So a higher compression ratio is good from a performance standard, but it also creates some other things you have to compensate for, like additional heat and things like that.